Welcome to the 44th lecture on computational mathematics with Sage Math. In this lecture, we will look at Google PageRank algorithm and how search engine works. So, if you look at the currently the internet users, for example, in India, over 700 million people use internet as of July 2020, and there are about 400 million active web pages in the world. So, one of the widely used activity over the internet is search. Most often when you search any keyword, you get the website which is the most relevant that appears as the first website. So, you should be wondering how does it work, how does it happen. So, actually it uses a very simple concept of linear algebra. So, we shall look at how it works and the concepts involved in Google PageRank algorithm. So, let us start with a simple internet network of 5 web pages A, B, C, D, E, and the arrow means there is a link from one website to another. So, for example, there is a incoming arrow at A from C. So, there is a link or hyperlink from the website C to A, right. Now, this network you can generate in Sage Math using digraph function, which is a package. Graphs is a package for graph theory. Sage is very good at graph theory, and digraph stands for directed graphs. So, you can plot this network using this digraph. So, what you are doing, you are saying that make a directed graph from nodes 1, 2, 3, 4, 5, and from node 1 you there is a link to 2, 4 and 5. From link 2 from web page 2 you have a link to web page 1 and 4 and so on, and you can relabel these nodes as A, B, C, D, E. That is what we have. You can, if you do not relabel, it will give you by default label as 1, 2, 3, 4, 5. So, let us run this and you will see a network. This graph is plotted randomly. So, the position of each of this node and the arrow may differ when you do this. For example, if I run this again, this may be slightly different from what you got earlier. Now, if you look at this website, and to each of this arrow you can assign to this network you can assign a matrix of 0 and 1s. So, if there is a link from j to I, we can say that the aijth entry of that matrix is 1, otherwise 0. That matrix is known as adjacency matrix, and Sage has inbuilt function to find adjacency matrix of any graph. So, here G was defined as a graph of vertices and edges. This is a directed graph. So, you can find adjacency matrix of this using G dot adjacency and then transpose. So, if you are taking ijth entry as 1 when there is a link between from I to j, then it will be adjacency matrix, but as I said we will look at ij entry is equal to 1 when there is a link from j to I. So, that is why we are taking transpose of this, right. Now, if you look at this matrix, this adjacency matrix, and look at the rows and columns. So, if you look at, for example, the rows, let us say look at second row. Second row corresponds to the node B. So if you look at the node B, you can see here there is a link from C to B, there is a link from E to B, and then there is a link from A to B. So if you look at this second row, then you can see here 1 C and D, 1 C and E. So those are the links. There is no link from C to B. So the row represents the incoming links, whereas column represents outgoing links. So for example, if I look at B, from B there is only one outgoing link to D. So the second there is one outgoing link to A as well, and there is one outgoing link to A and one to D. Therefore, second column will have entries A 1 2 as 1 and N 4 2 as 1, right. So this is how this you can interpret this adjacency matrix, right. Now this you can find out importance of each of this web page by the number of incoming links. So if you find out the sum of the links on each website, so the first website importance is 3 because there are 3 incoming links, and in this case fourth has maximum, which is 4, and the third one has only one incoming link, which is 1. So you can see here fourth website has maximum importance, whereas the third one has the least importance, right. Now in this case if you just simply look at the number of incoming links, etc., the many things are not taken into account. For example, the link from an important web page should matter more than link from mediocre web page, and also not all websites are connected. You can have two websites which are not connected. In that case, how do you look at that, right? And is there always a unique most important website? So there could be more than one website having the same importance. Then which one should appear first? And some pages do not contain any outgoing links. Such nodes are known as dangling nodes. So in that case, what happens? So these things are not taken into consideration if we simply look at the number of incoming links for importance of a website. So how does one take into account these things? So if you look at, for example, suppose we let us say xi denotes the importance of the scores of the web page I. When I say scores, means how many times you have the incoming links, and Ni is the number of outgoing links from the web page I. Then if you look at, for example, first node A, then it has incoming links from B, C and D, and number of incoming links from B, number of outgoing links from B is 2, from C it is 3, and from D it is 1 here, 1, 1, 2 and 3, right. So therefore in this case the x1, which is the importance of the scores at A, should be equal to x2 plus x3 plus x4. However, if I look at x2 has 2 outgoing links, so there is equal probability that it gives vote to A or to D. For example, from B you have outgoing links to A and to D. So there is equal probability that B votes to A or D, so therefore the probability is half. Therefore x1 will be now x2 divided by 2. Similarly x3 divided by 4. From x3 there are 4 outgoing links, and from x4 there are only 3 outgoing links. So this is x1 is equal to x2 by 2 plus x3 by 4 plus x4 by 3. Similarly you can do find this relation for the second node, that is B. For B you will get x2 is equal to 1 by 3, x1 plus 1 by 4, x3 plus 1 by 2, x5. From x3 will be x3 is equal to 1 by 3, x4, and x4 will be this, and x5 will be this. Therefore this set of equations reduces to x1, x2, x3, x4, x5 is equal to this, and that can be written as matrix times x1, x2, x3, x4. So you have this equations is written as linear equation Ax equal to x. So if x is a solution of this system of linear equations, it amounts to saying that x is eigenvector of A with eigenvalue 1. So in particular this problem reduces to finding eigenvector of this particular matrix, which generally we call as transition matrix or probability matrix with eigenvalue 1. Now if you look at finding eigenvalue eigenvector is not a big task, and also if you notice this in this matrix each column is sum is 1, therefore this is what is called column stochastic matrix. Similarly you can define row stochastic matrix. So and each entry in this is non-negative because it is a probability, right. So therefore you can define the importance of any kth node as summation x j upon summation n j, where what is nj? Nj is the number of outgoing links from j, and what is j varying over lk? Lk is the subset of 1 to n that denotes the set of incoming links, right. So actually this problem of finding the importance of any web page is amounts to, or it is equivalent to finding eigenvalue and eigenvector with respect to eigenvalue 1, and this stochastic matrix you can show that always has 1 as eigenvalue, right. So let us look at this again. So this problem you can also think of in the following way: if you somebody starts surfing the internet, then in long run where can you find him, right, after 1 click, after 2 click, after 100 clicks, after 1000 clicks. So it will give you what is his probability of being on a particular website. So how do we find that? So again let us look at the same network of 5 nodes. This is slightly better, same network of 5 nodes, and to this network we will associate a matrix which is called transition matrix, which I am calling as H. Hij is 1 if there is a link from j to I and 0 otherwise. So then this is the adjacency matrix, and then we will find the probability matrix or transition matrix attached to this network, that is actually each entry you divide by the sum of the entries in the column. So that is why it will be column stochastic matrix. So you can see here it is quite easy. You take the columns of H and divide it by this sum of the columns, entry in the columns, and do it for each entry, right. So this is the adjacency, this is the transition matrix associated to this network of 5 websites. Now suppose somebody starts from, let us say, second website. He starts surfing this particular network from second websites. So after 1 click, for example from the second website, after 1 click from second website you have 2 outgoing links, 1 to 1 and 1 to 4. So there is a half probability to be at 1 is half, probability at 4 also half, right. So after this, after that is 1 click, after second click this half, again from from website 1 you have 1 outgoing link, 2 outgoing, 3 outgoing links. So the probability will be half times 1 by 3 to here, half times 1 by 3 to here, half times 1 by 3 to here. So how do we obtain after 1 click? That you can obtain simply by multiplying this vector 0 1 0 0 0 by this matrix, that is the probability matrix or transition matrix. So if you say P into V, the probability of being on website 1 is half and on website 4 is half. If I look at what happens after 2 clicks, So then I will have to again multiply this by p. So p into this, which is p square v, that will give you probability on website 1 is 1/6, at 2 is 1/6, at 3 is 1/6, at 4 is 1/6, and at 5th is 1/3. So in general you can find what happens to this probability after, let us say, 100 clicks. After 100 clicks, the probability in decimal is like this, 0.2195 and so on, right. So you can see here in this case the maximum probability is here at the website 4th. So that is about 30% chance of him being at website 4th, and about 9% chance at website 3 and so on. So you can similarly you can look at, let us say, what happens after 1000 clicks. So after 1000 clicks, again you can see here this vector what you have got, that is again a stochastic vector, because some of the entries in this will be 1 and each entry is non-negative. So this is actually almost same as this, it may differ in after so many decimal places, but they are almost identical. So what it means is that in long run this will be the probability of him being on a particular websites, and that you can arrange in decreasing order. So for example the maximum is this, so that is the probability of it being at website 4 is 30 and so on. The second probability is this, so that is this, and then these two has almost equal probability, and then this is the last one, right. So that is how you can obtain the importance of the website. So now this you can translate into the internet, the keyword search. So if somebody gives a keyword for searching on Google, then what it will do, it will search all over the places on the internet, and wherever that keyword is obtained, it will look at all these links and rank accordingly to this right. So right, next you can look at, now in this case what it amounts to is that finding very large power of this matrix P. Now if you look at, this is only 5 website with network with 5 websites, but in general, as I mentioned, there are about 400 million websites which are active currently. So therefore you will be dealing with 400 million by 400 million matrix, and finding power of such a large matrix is just impossible. Even the very efficient computer will have problem. So therefore in that case one has to find this notion using eigenvalue, eigenvector diagonalizations, which we already spoke about, right. So and also now if you look at, for example, the power, let us say 1000 power of this matrix, transition matrix P, what you see is each column is the vector which you obtained here, the probability vector. This is what is called a stationary vector, and so each column will be actually eigenvector with eigenvalue 1. So in particular P to the power n converges. Now again you can ask, when does a matrix to the power n, you can think of this as sequence of matrix power, when does it converge? So there is a whole theory about convergence of this power of matrices. I will give you reference a little later, so you can go through that reference and learn about this convergence. For example, one of the criteria for any stochastic matrix to be convergent is that it should be a regular matrix, it should be a regular stochastic matrix. That is same as saying some power of P should have all positive entries, right. Now you can also have a situation where you have a dangling node. What is dangling node? Dangling node is one where you can go to some particular website, but after that there is no outgoing link from there. So for example, many times you click on an image of something on a link, and it opens in a separate website, and or you could have a link to a PDF file. When you open this PDF file, it opens in a separate browser or separate tab. In that case you may not be able to go from that there may not be any outgoing link. However, in actual practice what we do, we either we go back or we close that particular tab and open a new tab. So this we do, but in algorithm it has to be taken into account. So this is a dangling node, where you can see here that the node 5 is a dangling node. From 5 there are incoming links, but there is no outgoing link from web set 5. So if in this case, suppose let us look at, we find out adjacency matrix and the transition matrix of this this particular network, and in case we start from the website 3 and then look at what happens in long run. So you can see here all these probability of going at each website is 0, because it has got stuck at web page 5. So this is not going to work. We cannot find rank or importance of website using, in this case, using this particular way. So there must be other way of dealing with this. You can also have a situation of loop. So for example, if you look at this particular network, then if you see here, for example 2 and 4. So from 2 you can go to 4, and from 4 you can go to 2, and you cannot go anywhere else. So this is a loop. So now again in this case, if I start with some website, so this is adjacency matrix and this transition matrix, and if I start with some, let us say, second website, then the probability of being on second website is 1 and everywhere else it is 0. That again is not good. If I start with let us say website 1 and then see what happens after let us say some 10,000 clicks, then you can see here again the probability at second website is 0.5, at fourth website is 0.5, and remaining all 0, right. So in case you have dangling node or loop, this way of finding eigenvector with respect to eigenvalue 1 may not work, or this just finding the importance by taking the large power times the initial vector will not work. Okay. So so the question is, how does one deal with such things? Now Google, what it does, it deals with such situations by defining what is called Google matrix G, which is defined as weighted average of this transition matrix P and the matrix S, where S is a matrix whose all entries are 1 by n. So 1 by n, if all entries are 1 by n, where n is the number of websites in a particular network, it simply means that every website is connected to every other, right. So that is why the probability of each will be 1 by n, right. So this is how we modify now, or we update this transition matrix to this Google matrix, which is weighted average of P and S, and here alpha is known as damping factor. Alpha lies between 0 and 1. I should mention here alpha lies between 0 and 1. So generally Google takes this value, a damping factor about 0.85. I mean this has been obtained using I mean the large, by working with several values and coming up with something which works. So you can take alpha to be 0.85. So let us define this matrix S, which is one for the above network, which is a loop. This is S, and then let us define the Google matrix G, which is alpha times P plus 1 minus alpha times S, and take alpha to be 0.85, which is the damping factor. And then in this case this matrix reduces to this or updates to this. Now you can see here there is no 0 column. Now in this case, if I look at what happens after let us say 100 clicks, so then you will not get this 0. Of course in this case you can see here the probability of this being at web page 2 is high, and also at 4 is high compared to others, right. Instead of 100, if you make it 1000 click, then again you will see that this is what is you get as a stationary vector. Similarly, and you can rank this, you can rank these things using there is a option called sort. So you can sort this in reverse order, that is decreasing order, and then you can print this is the rank of all these websites sorted as decreasing order of the importance, and this is the web page number. So third website has maximum rank, followed by the next one which is the first one, and followed by the fourth one, and so on, right. So now you can look at, for example, if I have a large network, okay, if I have large network. So Sage has inbuilt function to generate a random graph. So let us say there is an option called random directed graph using some algorithm which is called GNM. So inside this digraph you have this option. So let us take, you have a website of 10 web pages, and then let us say there are 50 links, that means 50 edges. So you have a random network with 10 websites and 50 links, that is not very big, and let us say the define D to be the graph, and then let us ask it to show. When you show this, this is what you get. It looks somewhat complicated, not too much, right. Now what we can do, we will find out, let us say adjacency matrix to this, and then transition matrix of this website of this network, and then find this matrix S which is 1 by n for every I and j, and take alpha to be 0.85 and G to be that is Google matrix to be alpha times P into 1 minus alpha times S. Now if you see here, this alpha is equal to 0.85, what it means is that about 85% of the chance, 85% times the user follows this link, and 15% of times he uses either back click or close the website and go to new close the tab and go to new tab, that is what is called teleporting, right. So let us run this, and then let us again take a random vector. So how we are generating, take a random integer between 0 and n minus 1, because index starts from 0 and goes up to n minus 1 in this case, and take a vector which is 0 vector, and then at ith generate a random website number, and replace that ith entry which is 0 by 1. So in this case you see here, this is the last website, last but one website. If I do once more, this is now fourth website. So this is the starting place for the user, the user starts surfing from web page 4. Now let us find out what happens after 100 clicks. So after 100 clicks, this is what you get. This is the probability of each of this website, and then if you look at the one which has the maximum probability, that is the website which will appear first. So for example, in this case this seems to be the maximum. No, this one is the maximum, the fourth website, and instead of 100 clicks, suppose if I say let me just copy and then paste it in the next cell. If I say, let us say for example 1000 clicks, then again these two are almost similar. So this Google matrix, you can check that Google matrix is again a stochastic matrix. It will be column stochastic matrix. In fact, it is a regular column stochastic matrix. Therefore the nth power as n becomes large and large, this will converge, and this will give you the stationary vector, which is the eigenvector corresponding to eigenvalue 1. So this is what you get. So this converges, and you can again sort this and arrange this in decreasing order of the rank. So third website has maximum rank, followed by the fourth, then followed by the eighth, and so on. The first website has the least rank, the second website has the least rank. This is the fourth website actually. Index 3 is fourth website has link. So, I think I should say here, okay, this does not matter anyway, because this link which we have generated, it says there is one 0th website. So, this is this is how you can rank the web pages, and this is how this Google search work with the simple notion of eigenvalues and eigenvector. So, there are lots of other applications of linear algebra. In fact, linear algebra is full of applications in science and engineering, but we covered some of it, not all of them, and you can refer to books, some standard books on linear algebra. It will give you some other applications. For example, one book which you can refer is a book by Anton. This is linear algebra and its applications, and this has a chapter of about 20 applications. Right. For this more on Google search algorithm, you can look at this this particular article by Brian and Lees, which says about the $25 eigenvectors, linear algebra behind the Google, right. Or you can also look at the original paper by Brin and Page, who invented this Google search engine, and this is also available here. You can also look at, for example, for the convergence of these stochastic matrices, etc. You can look at this book on linear algebra by Stefan Friedberg and Arnold Insel, and then Lawrence Spence. So, these are some of references for studying more concepts in linear algebra and some of its applications. Okay, so let me stop here. From next lecture onwards, we will start looking at some concepts in numerical methods. Thank you very much.